So we'll just finish off by doing this one. Where does tan of theta all squared equal root or positive 3? So a couple things. Number one, normally when we're dealing with these trig equations and we have something where a trig function is all squared, the other way of writing it is like this. Tan squared theta equals 3. It's just a way of writing it without brackets, but that's what it means. It means the tan of theta all squared. So to get the tan of theta by itself, you would take the square root of both sides. And whenever you're solving an equation, you take the square root of a number. There's always two answers that are being looked for, and they are the positive and negative root. So in this case, we would use the unit circle. It tells us to use exact values, but you should remember by now that at pi on 3, at pi on 3, the coordinates are 1/2 comma root 3 over 2, and the tangent is root 3. So if you have a reference angle of pi on 6 radians, the tan of pi on 6 is root 3. And you can check that on your calculator. With your calculator in radian mode, which I am, if you do the tangent of pi on 6, you get that decimal. I'm sorry, I wrote pi on 6 again. Sorry, I wrote pi on 6, but I did say pi on 3, so need to fix that. But my calculator just showed me that when I put the pi on 6, that was wrong. But that angle is 60 degrees, which is pi on 3. And so now when you take the tangent of pi on 3, you will get the 1.73, which is root 3. Okay, so the calculator can be used to check your reference angles. Now, once again, we want to know where the tangent is positive and negative root 3. So now there's going to be answers in all four quadrants. And all four of those quadrants will have the same reference angle of pi on 3. Remember, that's the angle between the terminal arm and the x-axis. And we want to state our solutions between negative pi and positive pi. So if you start at 0 and you go to negative pi, that means you're going to go pi in a clockwise direction. And then if you go around to positive pi, starting at 0 and going to positive pi, that will have the same terminal arm as negative pi. So the fact that the domain is in radians, from negative pi to positive pi, tells us that our answers have to be in radians. And also notice that if there was an answer on the negative x-axis, we could only use negative pi, not positive, because it says that theta is greater than or equal to negative pi and only less than positive pi. But none of our answers will be on the negative x-axis. Our four answers will come from these four terminal arms. So the first one, I'll do this one in quadrant 3, okay? And you have to go from 0 in a clockwise direction to this terminal arm here. You are pi on 3 short of going all the way to negative pi. So we could get that angle, our first angle for theta, by taking the negative pi and adding the pi on 3. To add those, we need a common denominator of 3, so the negative pi would be negative 3 pi on 3 plus pi on 3, which is negative 2 pi on 3. So that's that first angle, the one in the third quadrant. Our next one will be the one in the fourth quadrant, which is just negative pi on 3. That's the angle in the fourth quadrant. The one in the first quadrant would be positive pi on 3. And the one in the second quadrant is pi on 3 short of pi. So we take pi minus pi on 3. Or 3 pi on 3 minus pi on 3, which is positive 2 pi on 3. So there are our 4 answers. That is where the tangent of each angle should equal either positive or negative root 3, positive or negative 1.732, etc. So we can check them. We already know the tan of pi on 3 works. Let's take negative 2 pi on 3. Gives us the right value. Okay, and that is positive because that's in the third quadrant. Using our cast rule, that's the t quadrant. Our next one was negative pi on 3. That gives us the negative decimal. Right? That was the one in quadrant 4. And then the last one we can check is 2 pi on 3. So you should never get your stated answers wrong. The only thing you may make a mistake on is not getting all the possible solutions. In this case, maybe you only take where the tan of theta is positive root 3 instead of the negative. Okay, so have to be careful with that. Okay, so let's go on then to 4.4. Should that be page 42 in your package? We're going to solve some more trig equations. We're going to look at algebraically solving first degree and second degree trig equations in both radians and degrees. Talk about verifying that a specific value is a solution to a trig equation. We'll identify both exact and approximate solutions of a trig equation in a restricted domain. And then we'll also be looking at the general solution of a trig equation. So again, a trig equation is an equation involving trig ratios. We're going to be solving these. And we're going to see that in some cases, in order to solve a trig equation, we will need to factor in order to do that. So let's practice doing some factoring involving trig expressions. The first one is a trinomial. Sine squared theta, which remember means the sine of theta all squared, minus 4 sine theta plus 3. Now, you can simplify the factoring of this by using some substitution. For example, if we let sine theta equal x. So wherever we see sine theta in that expression, we'll replace it with x. Remember, sine squared theta means the sine of theta all squared. So if you replace the sine theta with x, that'll be x squared, minus 4 sine theta, which again is x, plus 3. And then if you factor that trinomial, it'll be x minus 3, x minus 1. And then we would put the sine theta back in for x. So it'll be sine theta minus 3 and sine theta minus 1. So those are the factors in terms of sine theta. So you could definitely use this process to help you factor these trig functions that have 3 terms in them. But hopefully you get to the point where you can do it just by inspection. Looking at question B, in this case there's only 2 terms, but there is a common factor of cosine x. Each term has at least one factor of cosine x in it. So we'll take cos x out as a common factor, and that'll give us 2 cosine squared x minus 1. Remember, cos cubed x is the same as the cosine of x all cubed. If you divide it by one factor of cosine x, it'll leave you with cosine of x all squared, which again can be written as cos squared x. Question C is an example of a trinomial, so we will factor this one by inspection. Again, you could use substitution like we did for question A, but I'm going to do it by the method of inspection. So the front terms have to multiply to get 2 tan squared x, which means you'll have to have a 2 tan x and a positive tan x. The last terms multiply to get positive 1, and when we multiply out the two binomials, we have to get an inside term of negative 3 tan x, which will work if I put a negative 1 and a negative 1. The outer products will be negative 2 tan x, the inner products minus 1 tan x. That gives us our negative 3 tan x in the middle. Yeah. 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 No, because this cos cubed x is the cosine of x all cubed. And we're dividing that by cosine of x, or cos x to the power 1. So you're dividing powers with the same base. You subtract the exponents and keep the base the same. 3 minus 1 is 2, so it becomes cosine of x all squared, or cos squared x. Yeah? Okay. Question D is an example of difference of squares. You got a binomial. There are two terms there. Both terms are perfect squares with a minus sign in between. So remember, to factor difference of squares, you always get conjugates, same two terms, opposite signs in between. The square root of sec squared theta is the secant of theta. The square root of 4 is 2. One's a plus, one's a minus. You could have the minus in the first bracket and the plus in the second. It doesn't matter. That's difference of squares. Question E, again, is a trinomial that we will factor by inspection. The front terms multiply together to get cosecant squared theta. So each one will be cosecant theta. The last terms multiply to get negative 2, and when we multiply these out, we have to get a positive 1 cosecant theta in the middle, which means you're going to have a plus 2 in one binomial, a minus 1 in the other. Those will multiply together to give you negative 2. And if you multiply out the binomials, the inner products would be 2 cosecant theta. The outer is minus 1 cosec theta. They would simplify to give us plus 1 cosec theta. And the last one, there's a common factor of sine x there. Take that out, you will get cotan x minus 2. There's your factors. So we always look for a common factor first. If it's a binomial, check for difference of squares. If it's a trinomial, see if you can factor it by inspection. So now that we've reviewed the factoring, let's solve some first and second degree trig equations, starting with example 1, which is a first degree equation. Note the domain. Theta is between 0 and 2 pi. 0 would be included, 2 pi would not. This also tells us that our answers have to be in radians. And then it also says give solutions as exact values where possible. So to solve this equation, we are first going to get the sine theta by itself. So I rewrote the equation and I will get sine theta by itself. The first thing I would do is subtract the 3 sine theta from both sides. So on the left, 5 sine theta, take away 3 sine theta, leaves us with 2 sine thetas. Then I would subtract the 2 from both sides. And that leaves us with 2 sine theta equals negative 1. And my last step would be dividing both sides by 2. And so our solutions will come where the sine of theta equals negative 1/2. So I'm going to give you a formula sheet on one side with the unit circle on the back. Remember, when it comes time to writing any quizzes or exams for this, you will not be given the unit circle. You have to be able to recreate it. And we've been talking about that. Use the first quadrant, which you can get with your hand trick, and then apply our cast rule and the reference angle in order to determine what the solution could be in those other quadrants. Again, the front has the formula sheet on there, the same one that you would get when you're able to go in there. On the back is the unit circle. You can refer to it. We're not done here. This is all it waits to do. We're not done. So, let me open up my unit circle here. And we want to see where the sine of theta equals negative 1/2. So we can start by putting our cast rule in there. And that'll tell us which quadrant or quadrants we're in. We want to know where the sine of theta is negative. And that is in quadrant 3 or 4. So the way we did it before is we looked on quadrant 1 and found out where the sine of theta was 1/2. Remembering that sine of theta is the y value, and it equals 1/2 when theta is pi over 6. There the coordinates are √3/2, that's the cosine, comma 1/2, that is the sine. So again, that occurs when our reference angle is pi over 6. So that is our reference angle in the two quadrants where our answers will lie. So the answer in quadrant 3 would be pi on 6 cast pi. The pi would be written as 6 pi on 6. So that'll give us 7 pi on 6. And in quadrant 4, we're pi on 6 short of 2 pi. So 2 pi over 1 with the denominator of 6 would be 12 pi over 6. Minus a pi on 6 gives us 11 pi on 6. So there's our two answers, 7 pi on 6 and 11 pi on 6. And on the unit circle that I just gave you, you can also see that. The sine equals negative 1/2 here in the third quadrant where theta is 7 pi on 6. And over here in the fourth quadrant when theta is 11 pi on 6. So for any of your assignments, you can refer back to that unit circle that I just gave you to get your answers. When it comes time to a quiz or a test, though, you're probably going to have to do it the way we first did it, and that is by using the first quadrant, reference angles, and the cast rule. Okay, so on to the next page. Again, this is a first degree trig equation. We want to solve where 3 times the cosecant of x minus 6 equals 0. So we will start by getting the cosecant of x by itself. We'll add the 6 to both sides. We'll divide both sides by 3. And because our calculator only has sine, cosine, tan, right, the values on the unit circle are in terms of cosine, sine, and tan. We'll write this in terms of the primary ratio. The reciprocal of cosecant, again, is sine, and the cosecant of 2 is 1/2. So our answers will be where the sine of x equals 1/2. So in this case here, it's a positive value, positive 1/2, which means our answers would be in either quadrant 1 or 2. There's where our two rotation angles will be. And once again, the reference angle is the same as the previous example because we wanted to know.
Could I please get first responders to room 2064? Again, first responders to 2064.
Okay, so this again comes from the fact that at pi on 6, the coordinates are root 3 over 2 comma a half. So our reference angle is pi on 6, and will be in either quadrants 1 or 2, which gives us one answer as pi on 6. That's the one in quadrant 1. Our second one will be pi on 6 short of pi. So if we go 6 pi on 6 minus 1 pi on 6, that gives us 5 pi on 6. So there's our two answers. And if we look at our unit circle, the sign is positive a half in the first quadrant when theta is pi on 6. As well in the second quadrant, sine is a half when theta is 5 pi on 6. Remember, you can also use your graphing calculator to check this. If you take the sine of pi on 6, we should get positive a half, and we do, as well as the sine of 5 pi on 6. Works. You should never get these wrong. You can always check them. Yes? Oh, yes, thank you. The domain says we have to be in degrees, so we'll change that then to 30 degrees and 150 degrees. So we'll change the mode to degrees to do our checks. The sine of 30 degrees and the sine of 150. They both work. Okay. Number 3. This one is back in radians. 0 will be included, 2 pi wouldn't. Judah, what would we do first here? What would we need to do to solve this one? You got a thought? Yes, no, maybe? Yes, no, maybe? Can you give me an answer? Judah, can you give me an answer? Can you help him, Diego? What do we need to do? What would our first step be? Okay, but then we still couldn't get tan theta by itself because one term's a tan squared theta, the other is a tan theta. So you can't get tan theta by itself by doing algebra like that. Still won't get tan theta by itself. Chase? Yes, the F word in math. We're going to factor. Like we did at the start, right? This is a second degree trig function. So the front terms have to multiply to get tan squared theta, which means you'll need a tan theta and a tan theta. The last terms will multiply together to get plus 4, and the outer and inner products will have to get to negative 5 tan theta, which means we need a negative 1 and a negative 4. They will multiply together to get plus 4, and if you multiply out the outer and inner products, you're going to get minus 5 tan theta. So our solutions will come when each factor equals 0. This is no different than when you solved quadratics back in 20-1 by factoring. No different. You factored them, and then your solutions came when each factor equals 0. The reason that works is because if the first factor, tan theta minus 1 equals 0, it doesn't matter what the second factor is because it's 0 times something. That always equals 0, which is what we want. Same thing with the second factor. If that equals 0, it doesn't matter what the first factor works out to because anything times 0 will give you 0, which is what we want. So that's why the solutions will come when each factor equals 0. So we want to know where the tan of theta equals 1 and where the tan of theta equals 4. Give exact values where possible. There are spots on the unit circle where the tan of theta equals 1. And that is at pi on 4, because the sine and cos are the same values, so when you divide them, you'll get 1, and down at 5 pi on 4. If it was degrees, it would be 45 degrees and 225 degrees. But in this case, we need to be in radians, so it would be pi on 4 and 5 pi on 4. But there's nowhere on the unit circle where the tan of theta equals positive 4. Not there. So now we're going to have to give approximate solutions, and we're going to have to set up our xy axes, and we're going to have to use our cast rule. In this case, the tan of theta is a positive value, positive 4. So the cast rule tells us that tan is positive in the first quadrant and the third quadrant. There's where our terminal arms will lie. And to find the reference angle, we need to use our calculator in radian mode, because we want our answers in radians, and we need to go second function tan of 4. The calculator gives us the reference angle, the angle between 0 and pi on 2 radians. And because it is an irrational number, we need to round it, so I'll say 1.32, let's say 58. That's your reference angle. 1.3258. That is the angle between the terminal arm and the x-axis. So our first answer will be that angle, 1.3258. The second one is that many radians past pi. So I'm going to store this number into memory slot A. So when I check it, I've got it. Then I'm also going to add pi to it to get my second angle, 4.4674. Those are our two answers. They are approximate answers because we had to round them. But if I check them, and you should always check them in the original equation. So I'm going to store this number into memory slot B, my second answer. My first answer was in memory slot A. So you see, if I check this using the original equation, the tan squared theta means the tan of theta all squared. So to check this, I'm going to open a brackets. I'll take the tangent of alpha A. When you hit the tan button, one bracket opens, you put the A in there, close the bracket, then close the bracket on the tan of A, because we need to square that. Minus 5 times the tangent of alpha A plus 4. That should equal 0, and it does. Again, we've seen this before. Sometimes the calculator, instead of giving an answer of 0, it gives an answer that's very small. Negative 3 times 10 to the negative 12. So that is negative 0.0, and you'd have 11 zeros before you have the 3. Essentially, it's 0. So we just showed that our answer, which is the first quadrant answer, works. To check the third quadrant answer, which I put into memory slot B, I can just go and change all these A's to B. And you get the same answer, which is essentially 0. So We check those ones. Now we can check our other two answers, pi on 4. Do that first. That one actually gives us an answer of 0, which is correct. And then 5 pi on 4. You should never get your stated answers incorrect because you can always check them. The only thing you might do is miss some of them by not getting all the quadrants that you need. But the answers that you get, you should never get wrong because you can always check them on the calculator. This next one is in degrees. It says give exact values where possible, otherwise give approximate angle measures to the nearest thousandth of a radian. Once again, we would have to factor this. And because it's a trinomial, you've got a cos squared theta and a cos theta, we must factor it. You cannot get cosine theta by itself. So that's where we'll start. So the front terms multiply to get cos squared theta. The last terms multiply to get -2. And when I multiply out the outer and inner terms, I have to get a -1 cos theta, which means I need a -2 and a +1. So our solutions will come when each factor equals 0. So you let them both equal 0, and then you solve for cos theta. Now there is a spot on the unit circle where the cosine of theta equals -1. Remember, cosine is the x value, and it equals -1 right here at 180 degrees. That is the only place on the unit circle where the cosine of theta equals -1. When theta is 180 degrees, which we're going to use because our domain is in degrees. There is nowhere on the unit circle where the cosine of theta equals +2, though. If you try to find your reference angle, like normally you would set up your coordinate plane, you'd use your cast rule to see which quadrant's cosine is positive, but then when you go into degree mode and you go second function cos of 2, you get an error because it doesn't exist. There is nowhere on the circle or nowhere in math where the cosine of an angle will equal +2. And here's the reason why that is true. If you graph y equals cosine x in your calculator, so you can just watch this. Next chapter, we'll look more closely at the graphs of trig functions, what they look like, and we'll do transformations on them. But for now, I'm going to graph y equals cosine of x. I am in degree mode, so my windows will need to reflect that. I'll go from -360 degrees on the x-axis up to +360 degrees. I'm going to set my scale at every 90 degrees on the x-axis. And I'm going to change my y windows between -2 and +2. And you're going to see why I chose those windows when I hit graph. So this is what the graph of cosine x looks like. Basically looks like a wave. But the maximum value that this graph goes up to is +1. The minimum value it goes down to is -1. It never gets up to 2 or down to -2. That's why when you go second function cos of 2, you get an error because it doesn't exist. The graph of cosine only goes up to +1 and down to -1. And the sine will do the same thing. If in y2 I do the sine of x, you're going to see that it's also a wave. It just doesn't start in the same spot. It has the same max and min value, though, as cosine. this graph also goes up to 1 and down to negative 1. It never gets up to 2 or down to negative 2. So if you were told that the sine of theta equaled 2, you'd get the same thing, an error, when you went second function sine. Same thing if you went second function sine of 1.5 or 1.2 or negative 1.1. The graph never gets to those values. It only goes as high as positive 1 and down to negative 1. Now, the tangent is completely different. We're going to look at the graph of tan x next chapter as well as sine and cos. But just so you can see what the graph of tan x looks like, and I'm going to choose zoom fit here. The graph of tangent has vertical asymptotes. The first vertical asymptote is at 90 degrees, and it extends upwards forever. The closer that the angle gets to 90 degrees, the higher the value of the tangent will be. But it'll never get to 90 degrees. It'll just keep getting larger and larger. Okay, and you can also see that by, let's say, taking the tangent of 89 degrees. It's a big number. If you take the tangent of 89.5, it's even bigger. Tangent of 89.9, even bigger. Tangent of 89.99. But if you try and take the tangent of 90, you'll get an error. It doesn't exist. We have that on our unit circle. At 90 degrees, we have the infinity symbol there for tangent. So this is why, when you look at the graph, there's actually a vertical asymptote there at 90 degrees. The calculator doesn't draw a vertical asymptote, but it's there. And the closer that the angle gets to 90 degrees, the higher the value of the tangent of that angle will get. So this tells us that it's possible to have a value of tangent greater than 1 and less than negative 1. In fact, we already saw that today, I think. Yeah, the last one, where the tan of theta was positive 4. We got answers for that, because the graph of tangent does go up to a y value of 4 and much higher, but not for sine and cos. So the only answer for this one would be the one we found. There's no solution for the cos of theta equals 2. And we can check our answer by making sure that we are in degree mode, which we are. And I want to check to make sure that 180 degrees works here. So the first term is the cosine of 180, which is all squared. So I had to use a couple sets of brackets here. Minus the cosine of 180 degrees. Minus 2. And that equals 0. So that checks, right? We know our answer is correct. Okay, so for practice, we're going to do page 211 to 212, questions 5 and 7. I will post these solutions on Google Classroom so you can check your answers. Really important that you do these questions, though. Do the practice, because you guys have a quiz that you're going to be writing on Tuesday on this chapter. Okay, so the practice is important so that when it comes time for these quizzes and then when you write our trigonometry test, you're going to be much better prepared for those assessments if you do the practice. Okay, I'm also going to hand out directing words for you as well. So the other sheet I'm going to give you has a directing words on one side, the formula sheet on the other. We've been referring to these directing words because when it comes to the diploma exam, you have to follow the directing words. So we have been talking about them already, what the word algebraically means, what the word determine means, but there's more on here that I'll give you the sheet so you can refer to it as well. Okay? So do the assignment, check on Google Classroom. You guys have a quiz on Tuesday, March 7th.